So apparently, I started a slideshow. Hey, what's up? This is Dr. Aeronautics, and this is Orbiter Space Flight Simulator Tutorials, Part 11. I'm glad you're telling me that my computer's performance is slow. That's why I bought you in the first place. Man, if I keep getting distracted like that, we'll never get to this, because this involves more math, although not more difficult conceptually. Gosh dang it! What the heck? Okay, so if my computer doesn't explode, we are going to try and well, we're not going to try, but we're basically going to take off and contact dock with the International Space Station. This will be a quick, redundant flight to almost nowhere, in which we will circle and go in a circle and go in a circle and keep going in circles. But heck, what do I care? It's an orbit. At least I get to go 17,400 miles per hour. So we're going to proceed with the launch window determination that I told you guys I would be looking into and presenting. Okay, so the process of orbital rendezvous with the space station is determining a launch window and knowing exactly when to take off during that launch window to rendezvous. In real life, you wouldn't be concerned about the second part so much as the first part, but the way Orbiter is set up, I'm actually not going to determine the launch window and have that. We're going to determine that graphically, but we're going to determine the takeoff time mathematically. In real life, you would want days to go by before you dock with the space station because you have to check out systems. But because we have no systems to check out other than the flight dynamics, we can dock as quickly as possible. So what we're going to do is we're going to take off, and our goal is going to be within one orbit or 90 minutes, contact dock with the International Space Station. So I'm going to explain how we figure that out. So we basically have to take off and climb to the 60 kilometers that we go to, and 60 kilometers and 7,600 meters per second. We're going to call 7,600 meters per second quantity VF, and we're going to set it equal to that. They need to make drawing a little bit more convenient on computers. Okay, so we have the quantity to VF, and now we need to figure out the time that it takes to get to orbit. Now, due to gravity and atmospheric loss, we're going to cheat and consider that a not a constant. What would it be? Okay, I can't think of it now, but we're going to call it a quantity, TO, time to orbit, and that's going to equal a convenient 769 seconds. That's the time that it takes to get into our final rendezvous orbit. So we basically have these two quantities here. Now we're going to find our linear acceleration. That is a linear fit to the equation because it's complicated. Now we could use calculus and integrate the equation, but this is just a simple tutorial, and I don't want to get too in depth in the math because we'll be here forever. So acceleration is defined as change in velocity over time. So we then have VF over TO, which is going to be final velocity over time to orbit. And that is going to be approximately 9.883 meters per second squared. And a lot of you who know gravity are thinking, hey, that looks like he just cheated off gravity. That's not right. Well, it turns out that this quantity just happens to be 9.8 meters per second squared. That's our average acceleration over the entire ascent, not to mention the turn that we have to do. So now that we have this acceleration, we can find it out using the distance equation where our final position will be when we reach orbit. So we're going to call this, with the formula, d equals 1/2 at squared. Maybe we'll use proper syntax so that there's no whatever. So we have 1/2 at squared. T is going to be TO, time to orbit. We're squaring that, and we're multiplying it by 1/2 of A, which is going to be our quantity here, 9.883 meters per second squared. When we do that, we find the distance denoted by dA equal to 2,922 kilometers. This will be our downrange position in one dimension after we have gone through main engine cutoff into our final orbit. This is the point where we want to look up for a rendezvous. So now what we need to do is find where the International Space Station is going to be. And so now we need to get the velocity of the International Space Station. That's a constant because, for the most part, because it's orbiting. So VISS is equal to, for a given time, generally 7,700 meters per second usually. So this is going to be the usual velocity of the International Space Station. Again, not exact. We could use calculus and trending, but it's going to be a simple tutorial. And then we need to figure out how far the ISS will travel in that time. D is defined as velocity times time. Therefore, DISS, which is going to be the distance the ISS will move during our ascent, TO, is going to be 769 seconds times our, or rather the ISS velocity of 7,700 meters per second. And we find that DISS, the distance the International Space Station travels in our ascent, is 5,921 kilometers. Now this is going to be the distance the ISS travels as we're taking off. So now we have to figure out how close the ISS is going to be behind us before we take off. And in this case, it's going to be the difference of those two. So it's going to wind up being, we'll say D actual is equal to DISS minus DA. Actually, I can go ahead and add these in now. So our actual distance is going to be the difference of the distance the ISS travels and the distance that we travel. So D actual is equal to 2,000, and this is convenient, 999 kilometers. This means whenever our launch window is, it happened again. This means whenever the launch window is, we take off when the International Space Station is 2,999 arc kilometers from our location. And this number doesn't really help much because you're constantly tracking the position of the ISS, not the position relative to you. So we have to translate that now to a grid, and because the Earth is round, it has to be a polar grid. So what I ended up doing is looking for a formula that relates arc distance to the grid of latitude and longitude. And I couldn't find anything. So what I ended up doing was deriving a formula that takes a two-dimensional two-dimensional rectangular, a polar coordinate, and we'll convert that to a latitude and longitude readout. And I will demonstrate that shortly. So next we need to do is we have this very important and I misspelled it. This is supposed to be d-actual, not d-cap. There we go. D-actual is approximately 3,000 kilometers. So now what we need to define is we need one more quantity, and that is going to be the angle of intersection between the nearest line of latitude, which is going to be defined as the origin, and the inclination of the ISS orbit. This is going to be, if we look at the Earth, let's draw the Earth real quick. The Earth has an equator. Well, and it also has lines of latitude. So we're going to pick one of those lines of latitude, and it's going to be our origin. But orbits run in planes, and the plane is going to be inclined. So the angle between the latitude marker and the inclination angle is what I'm going to define now as theta. And theta is going to be used to determine the position, because you need a magnitude and a direction to define a vector. And that's what we're trying to do right now. So we have the d-actual, and what we also need is the IIA, the inclination intersection angle. And that's going to be dependent on the launch window situation. And that's going to be whenever the launch window occurs. If we were doing the launch window determination calculations, then we would be looking this up. But because we're going to solve it graphically, that won't be necessary. So we're going to have to do this calculation when we're sitting on the ground to determine when we're going to lift off. And we'll have about 3 hours ahead of time notice, which is plenty of time to get the ship ready for takeoff. So now that we have these two values here, which are very important, these are our two big values here, we now need to convert these into polar coordinates. And so I basically derive this from the arc length formula, which states that the arc length S of a sphere, or a circle, is defined as the angle in radians times the radius of the sphere or circle, in which case it is the radius of the Earth, which is equal to 6,371 kilometers. So that is the constant radius of the Earth value that we're using. So we have this formula here. We know S, we know R. By the way, S, the arc length, is going to be set equal to d actual. So this becomes d actual is equal to theta times the radius of the Earth. And we know both. So when we solve for simple algebra, we find that theta is equal to S over R. And this basically says that the angle swept out by that distance is going to be equal to the d actual divided by the radius of the Earth. And then we get an angle in radians. So then what we have to do, and I'm walking you through the derivation right now, is get this into degrees, because we measure latitude and longitude in degrees. So you now have to multiply by 180 divided by pi, the value of 180 divided by pi. This will convert your radian values into degree values, which you can then use. So now once you have this, you can then go to the final formulas. And when you're talking latitude and longitude, I'm going to, there we go. When you're talking latitude and longitude, you deal with trigonometry, because you have to convert the degree into a rectangular coordinate system. It's not fully rectangular, of course, because we're dealing with latitude and longitude, but it's fitting a rectangular coordinate system to a sphere. So what we find is that we need to multiply by some number, which is going to take the horizontal component of that. And in trig, that is going to be multiplied by, in the case of latitude, that is going to be cosine theta. And so this basically says only count the horizontal component of this value here. So cosine theta is going to be if we draw a triangle real quick, a right triangle, cosine theta is going to say, I'm only interested in this change. And that is the amount of left-right motion here. So we're only counting the left-right motion, which is latitude. And so the cosine theta is 1, its maximum value, when the angle is 0. And the angle, the theta that I am referring to, is the inclination intersection angle. And that is going to be used to determine our cosine theta, obviously with an angle of... so when the value of cosine theta of the inclination intersection angle, this is going to be 1, its maximum value, and naturally you would expect the greatest change in longitude. Oh shoot, I'm sorry. That's not latitude, that's longitude. There we go. So now you know that cosine, when the inclination intersection angle is 0, all of the change will be in the horizontal because there's no angle. And therefore you have a longitude difference. But then we have to do a latitude version as well, because that's only one of the two dimensions that we need. And the complement to cosine is sine theta IIA, which is the obviously the inclination intersection angle. I caught that just in time. Okay, so now we have these two formulas here. And we can now calculate a theta of both latitude and longitude difference. And then all that's left is to give our current position in longitude. So longitude current, longitude actual we'll call it, minus longitude calculated. And latitude, people need to stop naming things after the same letter, because now I'm going to have to denote it LA. Latitude actual minus latitude calculated. And that will give us the tracked position of the ISS when we take off. In other words, when the ISS crosses that position, we hit the gas. And that is going to determine the position. So we're going to work out one of these formulas here now, real quick. So I do a calculation and I find out that D actual is 2,999 kilometers. So let's go ahead and find the Kennedy Space Center. That's our runway. And it's going to be 2,999 kilometers in any generic direction that I like. To make things simple, we're going to use 270. Actually, no. We're going to use 225 degrees. I don't think we'll have an angle this steep, but this is what we're going to use. So we're going to check against this value here and make sure they match. So 225 degrees, which is going to be the angle of the intersection here, and then 2,999 kilometers is the distance. That sucks. I can't open another page. Okay, so what we will do now, we know D actual, we know this, so we say theta longitude is equal to D actual divided by the radius of the Earth. And when we do that calculation, we find S over R equal to 0.4707 radians. That is an angle that we're going to then multiply against 180 times pi, and we're going to get this in degrees. So 0.4707 times 180 degrees divided by pi. And then we find that the total angle is going to be equal to 26.97 degrees of arc on the Earth. So now what we have to do is multiply this value by cosine of the angle, which in this case is 225 degrees. So we do cosine of 225 degrees, and to get the latitude, sine of 225 degrees. There should be an equal component as defined by the right triangle, 1, 1, root 2, which means 1 and 1 equal 1 because of, well, identities. It's pretty straightforward. So now we multiply the value 26.97 multiplied by the cosine of 225 degrees equals a total longitude change of negative 19.07 degrees let's just call it d longitude. And that is the difference in longitude. And now we multiply 26.97 times the sine of 225 degrees. And we also find, as denoted by the laws, that it is also 19.07 degrees delta latitude. So, all that's left now is to take the values that we have for the Kennedy Space Center and subtract 19.07 from both. So let's find the Kennedy Space Center, and let's find the latitude and longitude. The latitude is going to be 28.58 degrees latitude, and 80.67 degrees of longitude. So now we subtract 28.58 degrees of latitude minus 19.07, and the new value should be located at 9.51 degrees north. And now we do the same for longitude. 80.67 degrees of longitude minus 19.07 degrees of longitude. Of course, 80.67 is actually a negative number because we're dealing with west. So rather negative 80.67 minus 19.07 yields a new longitude of 99.74 degrees west, or a latitude of 9 degrees 32 minutes north-ish, and a new longitude of 99 degrees 40 minutes west-ish. And we're going to find that now. So we're going to have to be very careful not to make the thing go away. But we're going to go down until it is 9 degrees 32 minutes. And we're going to go west to 99 degrees and 40 minutes. So we said 9 degrees, 32 minutes, 99 degrees, 40 minutes. This is the position under my cursor that we expect the ISS to be. Whoops. And it was only 121 kilometers off due to reasons that Google Earth is not perfect and the fact that the Earth is not a perfect sphere. So you can now see that the fact that we were only this much off after this much difference, that this clearly has to be the correct formula. And now we can use it to our advantage come takeoff. So we shall now go into the spacecraft and await takeoff for the ISS.